Ancient sailors crossed entire oceans, guided only by the stars. We are reconstructing the celestial maps that made these voyages possible, a process that reveals how humanity first connected our world. By the end, you will understand precisely how we piece together these lost sky charts from scattered historical clues. How did a navigator with no modern tools know his exact position in a trackless sea? What forgotten secrets are hidden in the star lore of vanished cultures? What does our own desire to explore owe to those first stargazers? A lone voyager stands on the deck of his canoe, his world reduced to the rhythm of the waves and the immense dome of the night sky. He feels the swell of the ocean through his feet, a language as familiar as his own breath. His eyes lift to a specific cluster of stars, a constellation his grandfather taught him to recognize, and in that moment, he knows the precise direction of his homeland. This was the reality for Polynesian navigators and for countless other ancient cultures who first dared to turn the heavens into a map. From the vast Pacific to the shores of the Mediterranean, humanity began a grand project of celestial wayfinding. They watched the predictable paths of the stars, noting which ones rose and set in fixed positions, marking the north, south, east, and west. They learned that the sky was not a random scattering of lights but a vast, rotating clockwork, and by reading its face, they could find their way across trackless seas. This was not guesswork. It was a sophisticated science built on deep observation and encoded into songs, stories, and intricate stick charts that represented ocean swells and star paths. This knowledge was a civilization's most precious cargo, passed carefully from one generation to the next. It was this foundational understanding, this first act of translating the cosmos into a guide, that laid the essential groundwork for every sky map that would follow. The desire to chart the stars was born from the simple, profound need to find a way home. That same star, Sirius, blazed over the deserts of Egypt, but there it told a different story. An Egyptian priest would watch for its first pre-dawn appearance, a moment known as the Heliacal Rising. This event was not just an astronomical curiosity. It was a divine signal, a celestial announcement that the Nile's life-giving floods were imminent. The entire agricultural cycle of a civilization was tied to the rhythm of a single star. This is the profound truth hidden within ancient star lore. The myths were not just fables. They were a functional language, a way of encoding vital information about time, direction, and survival into memorable stories. The Babylonians mapped the sky with incredible precision, creating star catalogs that linked celestial movements to earthly events, laying the groundwork for the zodiac. The Greeks wove tales of heroes and monsters across the constellations, but these narratives also served as mnemonic devices, helping sailors remember the positions of key guiding stars. In ancient China, court astronomers maintained detailed records, seeing the heavens as a mirror of the empire, where the orderly motion of the stars reflected the proper order on Earth. Historians of astronomy now piece together these systems, revealing how a story about Orion the Hunter might also be a seasonal marker for planting, or how the Pleiades cluster signaled the start of the sailing season in the Mediterranean. To understand these cultures, we must learn to read their symbolic language. The constellation was not just a picture, it was a chapter in a practical guide to the world. The science of observation and the art of mythology were not separate pursuits. They were two sides of the same coin, a unified system of knowledge that allowed humanity to navigate both the seas and the cycle of the years. So how do we translate this symbolic language back into a usable map? The key lies not in the stars themselves, but in the tools these cultures left behind. That stick chart, a seemingly simple lattice of palm ribs and shells, was in fact a sophisticated classroom. In the hands of a master navigator from the Marshall Islands, it became a dynamic model of the ocean itself. The curved sticks did not represent land, but the deep, rolling swells of the sea refracted around distant islands. The shells marked not treasure, but the precise rising and setting points of key stars. This was the physical key to a mental masterpiece known as the star compass. Picture the entire horizon as a circle, divided into 32 houses. Each house is not an empty slot, but is named for a specific star or constellation that rises or sets in that exact sector. The star Altair, for example, would always rise in one house and set in the house directly opposite. A navigator would memorize this entire mental grid. This perfect compass rose etched into the sky. He did not just know the stars as points of light, he knew their journeys from cradle to grave across the heavens. He would lie in the bottom of his canoe, feeling the rhythm of the ocean, and by observing just a single star's position relative to his vessel, he could instantly know his bearing. But the stars were only part of the story. The true genius of this system was its redundancy. When clouds obscured the sky, the navigator read the ocean itself. He learned to interpret the complex patterns of swells, sensing how they bounced off unseen islands far beyond the horizon. He watched the flight paths of birds. A certain tern flying out to fish in the morning would always return to its island home at night, revealing the direction to land. This was not a system of separate clues, but a single, unified language of the world. Wave, wind, bird, and star all spoke together, telling a continuous story of place and direction. This indigenous science, refined over countless generations, allowed for the deliberate settlement of islands scattered across millions of square miles of open Pacific. It stands as a monumental achievement in human history, a testament to a profound and intimate connection with the natural world, where every element of the cosmos became a signpost on an endless sea. While Pacific navigators mastered the sea through feel and memory, a parallel revolution was unfolding under the domes of medieval Islamic observatories. Here, scholars were translating the cosmos into mathematics. In the dim light of a lamp, an astronomer aligns a complex astrolabe, its brass plates etched with a precise model of the heavens. His goal is not just to find direction, but to measure the very slow wobble of the Earth's axis, a phenomenon known as the precession of the equinoxes. This meticulous work was part of a grand scientific tradition that preserved the knowledge of the Greeks, Indians, and Persians, and then expanded upon it with breathtaking rigor. These astronomers produced comprehensive books known as Zij, which were far more than simple star charts. They were detailed astronomical tables that catalogued the positions of stars, the movements of planets, and the timing of eclipses with unprecedented accuracy. The scholar Al-Biruni exemplified this approach, writing that the seeker of truth is not one who studies the writings of the ancients and follows them blindly, but rather one who questions and verifies everything through his own observation and logic. This empirical spirit led to the creation of powerful new tools for wayfinders. The camel, a simple yet brilliant navigational device, was one such innovation. It was a small wooden rectangle attached to a string with a series of knots. A sailor would hold the string at his teeth and line up the card with the horizon and a specific star, like the North Star. By using different knots, he could measure the star's angle above the horizon, giving him his latitude. This was celestial navigation reduced to its most practical and portable form. The work of these medieval astronomers provided the critical data and the refined instruments that would later fuel the European age of discovery. When Portuguese explorers began venturing down the coast of Africa and out into the Atlantic, they were not starting from scratch. They were building directly upon the precise star tables and navigational science meticulously compiled in the observatories and workshops of the Islamic world. The stars that guided a Polynesian voyager were the same ones measured by an Arab scholar, their light now quantified into numbers that could cross oceans. The precise star tables of the Islamic world arrived in Europe at a moment of explosive change. In a 15th century workshop, the scent of ink and damp paper fills the air as a cartographer watches a new page emerge from his wooden press. This is not a map of land but of the heavens, a celestial chart printed not by hand but by machine, its identical copies destined for ships preparing to sail beyond all known horizons. This was a revolution in knowledge as profound as the voyages themselves. The printing press transformed celestial navigation from a secret art into a standardized science. Before this, star charts were precious manuscripts, painstakingly copied by scribes, each copy susceptible to tiny errors that could multiply over miles of ocean. Now, for the first time, a navigator in Lisbon and a ship's captain in Venice could work from the exact same map, their data consistent and reliable. The work of astronomers like Regiomontanus was central to this shift. He and his peers produced detailed books called ephemerides, which were essentially calendars of the future. These tables predicted the precise positions of the sun, moon, and planets for years to come, allowing a navigator to calculate his longitude by comparing the predicted positions with what he observed from his ship. Think of it as a shared cosmic timetable, printed and distributed across a continent, synchronizing every explorer's watch with the clockwork of the solar system. This was the critical infrastructure for the age of discovery. When Columbus set sail, when Magellan planned his circumnavigation, they were not relying on vague rumors or ancient myths. They carried with them these printed guides to the stars, the collective knowledge of centuries now mass-produced and placed into the hands of adventurers. The printing press did not just spread information, it created a network of shared certainty, a common language of the stars that would ultimately weave the separate threads of human exploration into a single, connected globe. But how did these explorers actually use these beautiful new maps while their ships were tossed by violent, unknown seas? A Portuguese captain braces against the swaying deck of his caravel, his hands steadying a heavy brass disc. This is the mariner's Astrolabe, a portable observatory that transformed the abstract sky into a number he could record in his logbook. Its origins reach back to the ancient Greeks, but it was perfected in the workshops of the Islamic world, a tangible product of that earlier scientific revolution. The instrument was a masterpiece of engineering, a flat, circular device etched with a map of the sky known as a retrace. This was a complex web of pointers representing the brightest stars, all rotating over a plate engraved with coordinate lines for a specific latitude. A pivoting rule called an alidade acted as a sighting device. On land, the Astrolabe was a versatile computer for astronomers, able to tell time, calculate sunrise, and track planetary movements. But at sea, its purpose was singular and vital. The captain would suspend the Astrolabe by a ring at its top, letting it hang vertically. He would then sight along the alidade, lining it up with the sun at noon or with the pole star at night. The point where the alidade crossed the graduated scale on the rim gave him the celestial body's altitude above the horizon. This single number, the angle, was the key to his position. In the northern hemisphere, the height of the North Star above the horizon is almost exactly equal to your latitude. If the pole star appeared 30 degrees high, you were at 30 degrees north latitude. For the sun, the calculation was more complex, requiring reference to those printed astronomical tables, but the principle was the same. This simple act of measurement, repeated day after day, allowed a ship to sail a consistent parallel, to know with certainty how far north or south it had traveled. The astrolabe did not just measure the sky, it collapsed the immense distance between the heavens and the deck of a ship, translating the cosmic dance into a reliable, repeatable calculation. It was this very act of translation, this turning of starlight into data, that would soon demand an even more precise and universal language for the entire globe. Yet even the trusted astrolabe had a critical flaw. On the heaving deck of a ship, its heavy brass form would swing wildly in the wind, making a precise sighting of the sun nearly impossible and punishing the navigator's eyes with its blinding glare. The solution arrived in the form of a deceptively simple wooden stick. The cross staff, or Jacob's staff, was nothing more than a long main rod with a sliding cross piece. A sailor would place the end of the staff against his cheekbone and then slide the cross piece until its lower edge appeared to rest on the horizon while its top edge touched the star he was measuring. The cross piece's position on the graduated rod gave him the angle of the star above the sea. It was a clever geometric solution, turning a complex instrument into a tool of elegant simplicity. But this method still forced the navigator to stare directly at the sun, a practice that could damage his vision and lead to disastrous miscalculations. The relentless drive for safer, more accurate navigation sparked the next great leap, the Backstaff. True to its name, this ingenious device allowed a sailor to turn his back to the sun. He would hold the instrument and adjust a sliding vane until the shadow it cast fell precisely on a sighting slit that was aligned with the horizon. By measuring the sun's altitude using only its shadow, the navigator protected his eyes entirely. This was more than mere convenience. It was a fundamental shift that dramatically improved the reliability of celestial observations in the harsh marine environment. These two tools, the cross staff and the backstaff, represent a clear evolution, a direct response to the physical challenges faced by those who sailed. Each refinement, from staring at the sun to using its shadow, was a hard-won victory against the elements. This constant push for better data, for more precise numbers, was fueled by voyages that stretched further into the unknown, where a single degree of error could mean missing an island entirely or being dashed upon a hidden reef. The very safety of the ship and its crew depended on the accuracy of these angular measurements, forcing a continuous cycle of innovation that would soon demand a new kind of map, one that could standardize the entire globe. On a fog-shrouded night in 1707, 4 British warships, confident in their course, ran aground on the Isles of Scilly. Nearly 2,000 sailors perished in the cold waves, a catastrophic loss blamed not on a storm, but on a simple, fatal miscalculation. The admiral had believed his fleet was safely west of the islands, but his navigation was dangerously wrong. The ships were lost because no captain at sea could accurately know his longitude, his position east or west. This was the infamous Longitude Problem, the single greatest navigational puzzle of the age of sail, a challenge so immense that governments offered vast fortunes to anyone who could solve it. Why was longitude so much harder than latitude? Finding your north-south position was a matter of simple geometry, measuring the angle of the North Star or the noon sun above the horizon. But longitude is time. The Earth spins a full 360 degrees every 24 hours, meaning that for every hour of time difference between your local noon and a known reference point, you have traveled 15 degrees of longitude. If you knew it was noon in London but the sun did not reach its highest point aboard your ship for another 2 hours, you knew you were 30 degrees west of the British capital. The problem was keeping London time on a ship. The rolling, salty, temperature-swinging environment of a vessel at sea destroyed the delicate mechanisms of pendulum clocks within days. Without a reliable clock, a ship was literally lost in time. The brightest minds proposed fantastical solutions. The lunar distance method involved taking hundreds of complex measurements of the moon's position relative to stars, a process requiring clear skies and hours of calculation. Others suggested observing the magnetic variation of compass needles, a method that proved too irregular and unpredictable. The solution would not come from mapping the stars, but from mastering time itself. It arrived in the form of a series of intricate machines built by a self-taught English carpenter and clockmaker named John Harrison. He dedicated his life to creating a sea clock, or marine chronometer, that could resist the ocean's motions. His first model, H1, was a masterpiece of brass and wood, using counteracting balances to negate the ship's roll. But Harrison was a perfectionist, and he spent decades refining his designs, each new chronometer smaller, more resilient, and more precise. His fourth model, H4, looked less like a traditional clock and more like a large, ornate pocket watch. In a grueling sea trial to Jamaica, it lost only 5 seconds over the entire voyage, an error in longitude of just a few miles. It was a staggering achievement. Harrison had succeeded where astronomers and mathematicians had failed for centuries. He had built a portable, reliable keeper of time that could carry the precise hour of a home port to any corner of the globe. With a marine chronometer, every navigator could now hold a perfect, ticking reference of Greenwich or Paris or Lisbon in the palm of his hand, finally completing the celestial map and allowing humanity to pinpoint its exact location on the vast, empty face of the Earth. The sea holds its secrets close, but the scent of old vellum in a quiet archive tells a different story. A historian gently unrolls a fragile chart, its surface a spiderweb of lines radiating from central points like cracks in a pane of glass. This is a Portolan chart, a medieval sailor's practical guide to the Mediterranean world. Those intricate lines are not decorations, they are room lines, a direct path system that allowed a captain to set a constant compass bearing from one port to another. To draw one was an act of faith in accumulated experience, a testament to generations of pilots who had memorized headlands, harbors, and the feel of the currents. The accuracy of these coastlines, charted centuries before the marine chronometer, is startling. How did they achieve such precision without the tools we take for granted? The answer lies in a modern forensic investigation. Researchers now use multispectral imaging to peer beneath the surface of the parchment, revealing corrections and first drafts that were scraped away. They analyze the chemical composition of the inks to trace trade routes of materials, and they study the very animal skins used for the vellum, which can be dated and sourced to specific European regions. Each chart becomes a unique artifact of a living navigational tradition. A famous case is the Carta Pisana, the oldest surviving Portolan, drawn in the late 13th century. Its rendering of the Black Sea and the Mediterranean is so accurate that it rivals maps made 300 years later. This was not the product of celestial mathematics, but of countless logged voyages, of sailors calling out soundings and noting landmarks, of knowledge passed from pilot to apprentice in a continuous chain of practical wisdom. The names crowding the coasts are not just labels, they are a litany of safe anchorages and dangerous shoals, a coded logbook transformed into a map. These charts remind us that the first true maps were not drawn from a god's eye view, but from the deck of a ship, a record of where humans had safely sailed before. They represent a different kind of science, one built on memory, repetition, and a deep, intimate trust in the collective knowledge of those who knew the sea. A lunar eclipse was a celestial gift to a navigator lost in time. As the Earth's shadow began its slow crawl across the face of the moon, a sailor would start a sandglass. By timing the precise moments the shadow touched the moon's edges and then retreated, he could compare his local observation with predictions published in almanacs for a reference city like Paris or London. The difference in time gave him a rough idea of his longitude, but eclipses were rare events, and the open ocean offered no such guarantees. The more common and far more demanding technique was the lunar distance method. This required a navigator to measure the precise angular gap between the moon and a specific, bright reference star. The moon moves rapidly against the backdrop of stars, shifting its own width every hour. This movement meant it could function as the hand of a giant cosmic clock. If you knew the exact time in Greenwich and you measured the exact distance between the moon and the star Aldebaran, you could consult your pre-calculated nautical almanac. The almanac would tell you what that measurement should have been at that very moment in Greenwich. The difference between what your almanac said and what you observed with your sextant directly translated into your longitude. The calculations themselves were a formidable barrier. They could take a skilled mathematician up to 4 hours to complete, a process fraught with the risk of a single, tiny error rendering the entire effort useless. A navigator had to account for atmospheric refraction, which bent starlight, for the parallax of the moon, which changed its apparent position based on the observer's location on Earth, and for the instrument's own imperfections. He was essentially performing advanced spherical trigonometry on a moving platform, often in terrible weather, by the dim light of a lantern. This was the immense intellectual burden of exploration before the chronometer. A ship's captain had to be more than a leader of men. He had to be a competent astronomer and a human computer, translating the slow dance of the heavens into a single, life-saving coordinate. The lunar distance method was a brilliant, cumbersome workaround, a testament to human ingenuity in the face of a seemingly impossible problem. It was a direct conversation with the cosmos, but one that demanded absolute precision in both observation and thought. Christopher Columbus faced a silent rebellion in the very tools he trusted. His compass needle no longer pointed true to the North Star, a discrepancy caused by the slow drift of the Earth's magnetic poles. Confused and adrift in an ocean without landmarks, he had no choice but to turn his eyes upward, recalibrating his entire course by the fixed, unwavering clockwork of the constellations. This was the daily reality for the great explorers of the Age of Discovery. Their voyages were not simple dashes into the unknown. They were a constant, grueling application of every navigational method we have pieced together. They blended the ancient art of dead reckoning, which involved estimating position based on speed and direction sailed, with the newer science of celestial fixes. A ship's log from Vasco da Gama's journey to India reveals this delicate dance. His pilots would spend days guessing their progress by throwing a log overboard and timing its passage along the ship's side, a crude measure of speed. Then, on a clear night, they would take a reading from the Southern Cross or another guiding star, correcting the accumulated errors of their dead reckoning with a single, precious data point from the heavens. Ferdinand Magellan's expedition, the first to circumnavigate the globe, pushed these techniques to their absolute limit. His crew spent 38 days crossing the Pacific, a distance so vast it shattered their preconceived maps. Their food spoiled, their water turned foul, and their only constant guide was the sun by day and the unfamiliar southern stars by night. They were living the ultimate test of the sky maps we are now reconstructing, proving their life-saving value in the most dramatic circumstances imaginable. These men were not just adventurers, they were the frontline practitioners of a new global science, stitching together the continents with threads of starlight and human courage. These men were not just adventurers, they were the frontline practitioners of a new global science, stitching together the continents with threads of starlight and human courage. Their success and their survival hinged on the ability to translate the abstract lines of a celestial chart into a safe path across an empty sea. A Marshallese navigator feels his way home, his mind a living chart of wave patterns and star houses, while a European captain, 300 years later, trusts the brass sextant in his hands and the printed logarithm tables in his cabin. These two figures represent not just different techniques, but entirely different philosophies of understanding the world. The Western system, born from the Enlightenment, sought to objectify nature. It relied on instruments to measure, on mathematics to calculate, and on printed tables to standardize. Its great strength was its transferability. Any trained sailor could be given a chronometer and a nautical almanac, and with enough schooling, find his position. This system created a universal language of coordinates, allowing a ship from England to meet a ship from Spain at a precise point in the mid-Atlantic. But this power came with a profound limitation, a deep dependency. If the chronometer broke, if the sextant was lost overboard, if the precious almanac was ruined by seawater, the navigator was plunged into a terrifying void, stripped of his ability to wayfind. His knowledge was external, held in his tools and his books. In stark contrast, the indigenous system of the Pacific was internalized and holistic. The navigator's knowledge was not stored in an object but etched into his very being through years of rigorous mentorship. He did not see the environment as something to be measured and conquered, but as a partner in a continuous conversation. He read the ocean swells as a tactile map, interpreted the specific flight patterns of birds as a compass, and navigated by a star compass memorized so completely it was as instinctive as breathing. His system was resilient. It could not be broken or lost because it was him. Its limitation was the immense time and cultural isolation required to cultivate such a master, and its knowledge was often so deeply personal and contextual that it was difficult to translate into a global standard. So which system was more accurate? The answer depends entirely on your goal. If accuracy means arriving at a specific set of coordinates, then the Western mathematical model eventually proved more precise. But if accuracy means a guaranteed, resilient journey to a desired landfall across thousands of miles of open ocean, then the Pacific system had already achieved that for centuries. One system sought to plot a position, the other to ensure a successful voyage. This is not a story of one being right and the other wrong, but of two powerful, brilliant ways of knowing. One turned the cosmos into data, the other into a story. Both, in their own way, were maps that guided humanity home. A high-resolution spectrometer hums quietly in a climate-controlled laboratory, its laser tracing an invisible line across a 500-year-old parchment. This is not a map of land, but a faded sky chart, and the machine is reading a story in its chemistry that the human eye can never see. By analyzing the specific wavelengths of light reflected from the surface, the spectrometer identifies the unique molecular signature of each pigment. The deep blue here is not just a color, it is lapis lazuli, a precious stone ground into powder and carried along ancient trade routes from a single mine in Afghanistan. Its presence on a Portuguese chart tells a hidden history of commerce and the immense value placed on these celestial guides. This is the forefront of modern reconstruction, where technology acts as a time machine, peeling back centuries to reveal how these maps were made, used, and what their creators truly knew. Alongside the spectrometer, multispectral imaging is perhaps the most powerful tool in the archive. It uses specific wavelengths of light, from ultraviolet to infrared, to illuminate what has been lost to time. A chart that appears blank to our eyes might, under infrared light, suddenly reveal the ghost of a constellation, a line of ink that has faded to near invisibility but still absorbs light in a way the blank parchment does not. It can expose an entire first draft, a cartographer's initial thoughts that were scraped away with pumice stone to make room for the final, more accurate version. We are no longer just reading the map, we are reading the process of its creation. To anchor these discoveries in time, scientists turn to radiocarbon dating. A tiny, carefully taken sample of the vellum, perhaps from the edge of a chart, is analyzed for its carbon-14 content. This radioactive isotope decays at a known rate, acting as a clock that started the moment the animal whose skin became the parchment died. This test can verify if a map genuinely belongs to the age its style suggests, or if it is a later, perhaps deceptive, copy. Once these physical clues are gathered, the work moves into the digital realm. Researchers use sophisticated cartography software to take a scanned image of the ancient star chart and overlay it with a precise modern plot of the celestial sphere. They can digitally stretch and warp the old map, correcting for the parchment's shrinkage over centuries until its star patterns align with our own databases. This precise alignment allows them to do something remarkable: calculate the exact date the map was intended to represent. Because of the slow precession of the Earth's axis, the position of the North Celestial Pole drifts over a cycle of 26,000 years. If the map's depiction of the stars around the pole is off by a specific, measurable amount, that error is not a mistake, it is a timestamp. It tells us the map shows the sky as it appeared in the year 1420, not as it looked in 1520. These technologies form a powerful bridge connecting the tangible artifact, the feel of the vellum, the smell of the old inks, with the intangible certainty of digital data. They are revolutionizing our understanding, transforming ancient sky maps from beautiful artifacts into precise, readable records of human observation, allowing us to witness the exact same stars that guided a navigator into the unknown. The star compass in the navigator's mind was his only true guide for a voyage of over 2,500 miles. We can reconstruct a legendary journey, the settlement of Hawaii from the South Pacific, by applying the very principles these master sailors lived by. Start with the season. Historical climate models suggest a departure around May, a window that offered favorable trade winds and a lower chance of encountering the violent storms of the winter months. The course was set north, a direction known as Hema, but this was not a simple straight line. The navigator would have aimed for a specific star house just east of north, steering by the constellation most closely associated with that bearing. His guiding star for the initial leg would likely have been Sirius, the brightest star in the sky, which in that season set almost directly in the west. He would keep the stern of his double-hulled canoe aligned with the setting point of Sirius, knowing this would push him steadily northward. For latitude, he watched the North Star, which his ancestors called Hokupa, the immovable star. As the weeks passed, he would note its slow climb higher in the heavens, a celestial altimeter telling him how far he had traveled from his tropical home. But the sky was a dynamic map. Each night, as the Earth turned, different constellations would rise and set, each one a familiar signpost. The Pleiades, known as Macaulae, would appear, and the navigator would note their position relative to his course, constantly cross-checking his mental chart. He did not sail by a single star, but by a rolling sequence of them, a celestial parade that moved with him across the ocean. The challenge was not just direction, but persistence. The voyage would take approximately 3 to 4 weeks. For all that time, the navigator and his crew would be exposed to the full fury of the open Pacific. They would face days of overcast skies when the star compass was wiped clean. In these moments, he would turn to the ocean itself, reading the long, rolling swells that marched endlessly from the east. He would feel their rhythm through the hull, a steady pulse that held its direction even when the sky was dark. He would watch for birds, knowing that the golden plover flew north to Hawaii during this very season, their flight path a living confirmation of his course. The greatest test came near the end of the journey. Hawaii is a tiny target in a vast ocean, a chain of islands invisible until the very last moment. The navigator would begin looking for the signs, the cloud formations that pile up over high volcanic peaks, and the specific patterns of ocean currents deflected by land. The smell of vegetation on the wind, the sight of certain land-nesting seabirds flying out at dawn, these were the final clues that his celestial map had led him true. When the green peaks of the Big Island finally broke the horizon, it was not a lucky guess. It was the culmination of a precise and ancient science, a journey plotted in the stars and confirmed by every sense. This reconstruction is more than a historical exercise. It is a testament to a system of knowledge so complete that it could populate the last uninhabited corners of our planet. A sudden blaze in the night sky could shatter a navigator's entire world. For cultures that depended on the stars remaining fixed and predictable, the appearance of a brilliant new star was more than a marvel, it was a crisis. Imagine the confusion aboard a ship when a star, one not on any chart, burned brighter than Venus for weeks on end. This was the reality in July of 1054, when a supernova now known as the Crab Nebula erupted in the constellation Taurus. Chinese and Arab astronomers recorded it in meticulous detail, calling it a guest star, visible even in broad daylight for 23 days. For a navigator steering by a star compass, this new, intense light in a familiar sector of the sky would have been deeply disorienting. His mental map, built on generations of observation, now contained a glaring, temporary error. Was it a new signpost or a warning to turn back? Such events forced a temporary reliance on other methods, on the sun by day, and the feel of the ocean swells by night, until the heavens return to their familiar order. Comets provoked a similar, if not greater, unease. Their unpredictable paths and ghostly tails were seen not as astronomical phenomena, but as divine messengers. A comet streaking across the established paths of the constellations was a tear in the very fabric of the cosmic order. For a society about to launch a long voyage, such an omen could delay departure for weeks, as priests and rulers debated its meaning. The sky was not just a tool, it was a living text, and these unpredictable events were paragraphs written in a sudden, urgent hand. They revealed the limits of human control, reminding even the most skilled navigator that his science existed within a cosmos capable of profound and beautiful surprises. This duality of reliable clockwork and awe-inspiring mystery defined the ancient relationship with the heavens. The navigator did not just use the stars, he lived within a story they told, a story that sometimes took a sudden and dramatic turn. That quiet beach at night was a classroom without walls. Under a canopy of stars, a father would point to a specific constellation, not just naming it, but singing its story and its relationship to the ocean swells. He was teaching his son to see the sky not as a random collection of lights, but as a living, breathing map. This intimate transfer of knowledge was the fragile thread upon which entire voyages depended. In the Pacific, this wisdom was encoded into chants and songs. These were not simple poems, they were dense technical manuals set to rhythm, making them easier to memorize. A single chant could list dozens of stars in sequence, describe the feeling of specific ocean currents near an island, and even name the guiding birds for that sector of the sea. The melody itself was a mnemonic device, its rhythm mirroring the roll of the waves. This knowledge was so precious that it was often kept within a single family line, passed from a master navigator to a chosen successor after years of rigorous testing. The student learned not from a book, but by doing, by lying in a canoe and feeling the swell patterns, by spending nights on the open ocean until the star compass was etched permanently into his mind. This oral tradition was incredibly resilient, but it was also vulnerable. A single broken link in the chain, a master navigator lost at sea without an apprentice, could erase centuries of accumulated wisdom from a community forever. Across the world, in the great port cities of the Arab world, navigational knowledge took a different form. Here, the science of the stars was written down in detailed manuals called romangs, or books of routes. These texts were comprehensive guides, blending celestial observations with practical sailing directions. A romang would describe the coastlines, note the depths of harbors, list the altitudes of key stars for different latitudes, and warn of seasonal monsoon winds. This written tradition allowed knowledge to travel beyond a single family or even a single generation. A pilot from Oman could sail to India using a manual written in Basra a century earlier. The challenge, however, was accuracy in copying. Every time a scribe hand copied a manuscript, small errors could creep in. A star's altitude miswritten by a single degree, a harbor's description slightly altered. Over decades, these tiny mistakes could multiply, leading ships dangerously off course. The European approach, supercharged by the printing press, sought to solve this very problem. With printing, a set of standardized sailing directions, known as a routier or a wagoner, could be produced in hundreds of identical copies. Every ship's captain now had access to the same information, corrected and updated by the most recent voyages. This created a powerful, collective intelligence that accelerated exploration. Yet, for all its power, this printed knowledge was external. It created a navigator who relied on his book and his instruments, rather than one who carried the entire map within himself. Each method, from the secret chant to the printed manual, was a response to the same fundamental challenge. How do you preserve a complex, three-dimensional understanding of the world and pass it on to the next person who dares to sail beyond the horizon? The success of this transmission meant that a discovery made by one sailor did not die with him, but became a permanent part of humanity's shared atlas, a legacy written in starlight and passed from one hand to the next. The words, "Here be dragons," may be a myth, but the sentiment was brutally real on a medieval chart. Across the vast, empty Atlantic, a cartographer might inscribe the phrase, "Mare tenebrarum," the sea of darkness. This was not a simple label, it was a warning woven from equal parts classical legend, religious dogma, and genuine fear. The map was not just a tool, it was a document of the known world's edge, and beyond that edge lay a realm where the sun was said to boil the sea, and monstrous leviathans awaited any ship foolish enough to venture further. This mythological barrier was a powerful psychological force, one that actively discouraged exploration for centuries. Yet, on that very same parchment, the depiction of the Mediterranean coastline could be startlingly accurate, a product of hard-won empirical knowledge from generations of sailors. This is the central paradox of these historical documents. They were a bizarre but functional hybrid of precise observation and pure fantasy. The constellations, for instance, came loaded with ancient baggage. Ptolemy's classical 48 constellations, inherited by European mapmakers, were not just neutral star patterns. They were the heroes and monsters of Greek myth, permanently fixed in the heavens. A navigator steering by the hero Perseus was also reminded of the sea monster Cetus, a celestial story that mirrored the very real terrors he believed lurked in the deep, uncharted ocean. The mapmaker was not just a scientist, he was a storyteller, blending the measured positions of stars with a cosmic narrative that explained the world's dangers. To understand the navigator's mindset, we must learn to read both layers at once. He trusted the star Altair to guide him from one known port to another, but he also fully believed that sailing too far west might cause him to sail right off the edge of a flat world or into the mouth of a biblical beast. His reality was a shifting line between the measurable and the unimaginable. Every voyage was a test not just of his skill, but of his courage to push against the boundaries of the myth itself. The map told him where to go, but its blank spaces and illustrated horrors told him where not to dare. This delicate balance between the charted star and the uncharted terror defined an entire age of exploration, until a new generation of sailors finally decided to sail directly into the heart of the darkness, armed with little more than improved celestial maps and a desperate hope that the old stories were wrong. A captain stares at his compass in the cold Atlantic dawn, the needle pointing stubbornly west of the pole star he trusted the night before. This discrepancy, known as magnetic variation, was a constant and puzzling companion for every navigator who relied on the new magnetic compass. The compass itself was a revolution, a simple floating lodestone in a bowl of water that evolved into a precise instrument mounted on gimbals to stay level on a heaving deck. Its genius was its constancy. When clouds blotted out the sun and stars for days on end, when the world was nothing but gray sea and gray sky, the compass needle remained, offering a steady, humming direction that never wavered. It transformed navigation from a fair-weather art into an all-weather science. Yet its guidance came with a cryptic code. Navigators quickly learned that the magnetic North Pole was not the same as the true North Pole defined by the Earth's axis. The difference between them, the variation, changed not only with your location on the globe, but also slowly over time as the magnetic poles themselves drifted. A compass reading in the English Channel was useless without knowing the local variation charted for that specific stretch of water. The problem grew even more complex inside the ship itself. The very iron used to build the vessel, from the nails to the cannon, could pull the compass needle from its true magnetic reading, creating a second error known as deviation. A captain had to become a detective of his own ship, carefully recording how the compass reading changed as he swung the vessel through a full circle, creating a deviation card that was as vital as any star chart. So how did they reconcile the magnetic world with the celestial one? The answer was a continuous act of translation. A navigator would take a bearing from the compass, then consult his charts to apply the known variation for his latitude. He would then correct for his ship's personal deviation. Only then did he have a true direction, one that could be checked against the unwavering positions of the stars. The compass did not replace the heavens, it conversed with them. The stars provided the absolute, eternal reference frame, the bedrock truth against which all other instruments were calibrated. The compass provided the minute-by-minute, mile-by-mile guidance through fog and storm. It was the perfect partnership, a dialogue between the magnetic heart of the planet and the cosmic clockwork above, making every voyage a testament to both earthly ingenuity and celestial faith. The ship's logbook was a testament to faith in numbers, a daily ritual of disciplined guesswork. Each entry recorded the vessel's speed, measured by heaving a log line over the stern and counting the knots that ran through a sailor's fingers in a half-minute glass. The captain would plot this estimated speed, and the compass direction sailed onto his chart, marking a new position each day. This was dead reckoning, the art of navigating by deduction and hope. It was a continuous calculation, a line drawn across the ocean based on the belief that the winds and currents had behaved as expected. But the sea is a realm of constant deception. An unrecorded current could push the ship miles off course overnight. A sustained gale could make speed estimates wildly optimistic, and the magnetic compass itself could lie. Over a week, these tiny, accumulating errors could conspire to place a ship dozens of miles from where its logbook claimed it was. The only way to shatter this illusion was to look up. The most crucial moment of any day was local noon, when the sun reached its highest point in the sky. The navigator would ready his backstaff or sextant, his back turned to the blinding sun, and measure its exact altitude above the horizon. This single number, the noon sight, was a moment of pure truth. By consulting his printed tables, he could translate that angle into his precise latitude. The sun's peak cut through all the uncertainties of dead reckoning, providing an undeniable north-south coordinate. For longitude, the process was far more demanding. If the navigator possessed a marine chronometer, he would compare his local noon with the time shown on that precious clock, which was set to the home port. Every hour of difference meant 15 degrees of longitude, but before the chronometer was widespread, he relied on the moon. The lunar distance method required him to measure the gap between the moon and a bright star, then spend hours with logarithmic tables to work through the complex math, a calculation so prone to error it was often called lunacy. This delicate dance between estimation and celestial truth defined life at sea. Dead reckoning was the continuous thread of the journey, while the celestial fix was the needle that periodically tugged it back into alignment. The navigator lived in a cycle of building confidence and sudden correction, his path across the ocean a zigzag of human intuition, forever being straightened by the cold, precise geometry of the heavens. The principles that guided a wooden canoe across the Pacific are now steering a 300-ton laboratory through the void. The International Space Station orbits our planet, a silent vessel navigating the ultimate ocean of space, and its course is plotted using a language of the stars refined over millennia. Astronomers today do not use a star compass with 32 houses, but they use a direct descendant of that idea, a global coordinate system etched onto the celestial sphere. This system uses right ascension and declination, terms that sound complex but represent a simple, powerful evolution. Declination is essentially celestial latitude, measuring how far north or south an object is from the cosmic equator. Right ascension is celestial longitude, measuring how far east an object lies along that equator. Instead of tracking the journey of a star from horizon to horizon, modern science pins every star, galaxy, and nebula to a fixed address in the sky using these two coordinates. This is the legacy of the first navigators, a system that transformed the heavens from a personal guide into a universal map. This same legacy is embedded in the technology you likely use every day. The Global Positioning System, or GPS, in your phone or car is a perfect echo of the ancient navigators' challenge. It solves the same fundamental problem, determining your precise location, but it uses a constellation of human-made stars orbiting satellites instead of natural ones. Just as a sailor measured the angle of the pole star to find his latitude, your phone measures the tiny time delays in signals from multiple satellites to triangulate your position on Earth. And just as John Harrison's marine chronometer provided the essential time reference to solve the longitude problem, every GPS satellite carries an incredibly precise atomic clock. The entire system is a breathtaking fulfillment of that ancient quest for a reliable, global fix. The algorithms that guide our ships, planes, and even our robotic rovers on Mars are written in the language of celestial mechanics, first decoded by those who dared to use the stars as a map. The legacy of the first global navigators is not confined to history books. It is woven into the very fabric of our connected world, a silent testament to the human drive to find our place in the cosmos. A star chant holds the power to guide a voyager home, but in the hands of an outsider, it risks becoming a stolen song. the modern effort to reconstruct these celestial maps forces us to confront a profound ethical dilemma. When a Western researcher studies a sacred navigation chant or deciphers the meaning behind a secretive stick chart, they are handling more than data. They are touching the intellectual and spiritual heritage of a living culture. For generations, this knowledge was a closely guarded treasure, passed orally from master to a single, chosen apprentice. Its secrecy was not about exclusivity, but about survival, the literal survival of entire communities who depended on its flawless transmission across the trackless sea. The act of publishing such knowledge in a journal or presenting it in a documentary, no matter how well-intentioned, can feel like a final act of colonial extraction, taking the last thing that was never offered. So who truly owns this wisdom? Is it the global scientific community, eager to complete the puzzle of human exploration? Or is it the descendant communities for whom this knowledge remains a sacred, living tradition, a core part of their identity? The answer is not simple, but a path forward is emerging through collaboration. Ethical reconstruction is no longer a solitary pursuit in a library. It requires forming genuine partnerships with cultural practitioners, the master navigators and knowledge keepers who are the rightful heirs to this legacy. This means stepping back and letting them lead, ensuring they have the final say over what is shared and what must forever remain within the community. It means acknowledging their contribution not as informants but as co-researchers and co-authors. This work shifts from taking to listening, from deciphering to being taught. The goal is not to possess the knowledge, but to help preserve it in a way the community itself chooses, perhaps by creating digital archives they control or by supporting programs that teach the next generation of navigators in their own language. Navigating these ethical waters requires the same careful attention as plotting a course by the stars, a constant correction to ensure we are honoring the source of the light that guides us. A fire in the Great Library of Alexandria did not just burn papyrus and ink. It consumed entire constellations of human knowledge, leaving behind a silence that no modern technology can ever fully penetrate. This is the historian's quiet frustration, the dead end that every reconstruction project eventually faces. For all our spectral imaging and chemical analysis, the historical record is, by its very nature, a collection of fragments. A single waterlogged manuscript rescued from a shipwreck might give us the star altitudes for a voyage from Aden to India, but the companion text that explained the accompanying wave law has long since dissolved into the sea. We are left with a precise number but no understanding of the living context that gave it meaning. The chain of copying introduces another layer of doubt. A medieval monk diligently reproducing a Greek star catalogue might misread a numeral, turning a declination of 20 degrees into 22. A single slip of the pen, repeated across generations of manuscripts, could steer a century of navigators subtly off course, their error born not of ignorance but of a scribe's tired eyes. Perhaps the most difficult limitation to overcome is the bias we bring from the present. We look at a Marshallese stick chart and see a map because our culture defines maps as physical objects. But to its creator, it may have been less a chart and more a mnemonic trigger, a physical aid for a mental process so deeply internalized that the object itself was almost incidental. We search for precise coordinates where the original navigator thought in terms of stories, of sequences, of relationships between elements we now classify as separate, like bird behavior and star paths. The stark truth is that not every line on a Portolan chart has a definitive explanation, and some of the most sophisticated techniques, perfected over lifetimes of observation, died with their last practitioner. Accepting these gaps is not a failure of historical method, it is a necessary part of the process. it is a humbling reminder that the past holds its secrets close and that the silent spaces on our reconstructed maps are not empty. They are filled with the ghosts of lost knowledge, a permanent and beautiful mystery at the heart of the human journey. A future blackout of our digital sky is not a far-fetched fantasy. Military strategists have long understood this critical vulnerability, training their naval officers in the use of the sextant not as a historical curiosity, but as a vital failsafe. In an age of electronic warfare and potential satellite disruption, the ability to fix a ship's position using the sun and stars transforms from an archaic art into a non-jammable, non-hackable life insurance policy. This is not just about having a backup, it is about maintaining operational sovereignty when an adversary can simply turn off the global positioning system with the flick of a switch. The same logic applies to the modern mariner, whether on a container ship or a private yacht. The international standards for sea training now strongly emphasize the retention of celestial navigation as a core competency. Why? Because a complex cascade of failures is always possible. A severe solar flare, a catastrophic power loss, or even a simple lightning strike could silence every screen on the bridge in an instant. In that moment of silence, the navigator who can step out onto the deck with a sextant and a nautical almanac holds the power to guide his vessel and its crew back to safety. This is not a rejection of progress, but a profound embrace of resilience. It recognizes that the oldest map of all, written in starlight, is immune to power outages and software glitches. Beyond pure necessity, a quiet revolution is underway among recreational sailors. For them, picking up a sextant is not about preparing for doomsday, it is about reclaiming a profound connection. It is the joy of solving a tangible puzzle that links them directly to the voyages of Cook and Bligh, a tactile experience in a world of intangible data. It forces a slower, more observant pace, where you become attuned to the rhythm of the planets and the slow turn of the constellations. This growing movement sees celestial navigation not as a useless skill, but as the ultimate form of mindful engagement with the natural world. The knowledge we have so carefully pulled from dusty archives and fading chants may, in the end, prove to be one of our most crucial inheritances. It is a timeless thread of wisdom, waiting in the wings, ready to guide us home when the artificial stars we have built for ourselves suddenly go dark. The ocean at night is an immense, breathing darkness, and on a 16th century caravel, one person holds its entire secret. He is the navigator, standing his watch under a sky salted with stars, the weight of 200 sleeping souls resting on his ability to read their cold, distant light. His work demanded more than mathematical skill. It required a specific state of mind, a fusion of unshakable confidence and profound humility. He had to trust his calculations against the terrifying evidence of an endless, empty horizon. In a gale, when the ship pitched violently and the deck was lashed by freezing spray, he still had to steady his astrolabe or backstaff, his mind calmly performing geometry while his body fought for balance. This was not a profession for the doubtful. Every decision, from altering course by a single degree to holding firm for another week, was a gamble with lives and a king's fortune. The stress was a constant companion, a tightness in the chest that only eased with the sight of a long-sought landmark. Loneliness was another. Surrounded by a crew who saw his art as near sorcery, he could not share his deepest fears or his moments of uncertainty. His authority depended on an aura of infallibility, even when he was secretly recalculating his position for the third time, praying for a break in the clouds. Yet within this isolation lay the reward, those rare moments of sublime connection. On a clear, calm night, with the celestial clockwork turning perfectly above and the ship cutting smoothly through bioluminescent waves, he was not just a technician. He was a participant in a cosmic dialogue, a tiny but conscious part of a universe that was vast, orderly, and breathtakingly beautiful. In those silent hours, the mathematics melted away, replaced by a feeling of rightness, a harmony between the ship's path and the paths of the heavens. This was the Navigator's true compass, an internal gyroscope of courage, patience, and intuition. To understand the maps they used, we must also understand the spirit of the people who dared to trust them, the human element that turned starlight into a path across the world. That final, silent moment of connection between the Navigator and the stars is the true legacy we have been reconstructing. It is a legacy written not in one language, but in many, a testament to humanity's collective genius. We have journeyed from the star houses of the Pacific, where the sky was a compass etched into memory, to the brass astrolabes of medieval scholars who translated the cosmos into mathematics, and onward to the printed charts that standardized the heavens for a waiting world. Each culture, in its own way, looked upon the same dome of night and found a unique path through its mysteries, driven by the same profound need to explore, to trade, and to find a way home. This was not merely a technical achievement, it was one of our greatest intellectual adventures, a grand project that connected the globe long before the first satellite ever blinked in orbit. As you look up at the night sky, you are seeing the very same map that guided the first global navigators. The stars have not changed, only our way of reading them. That shared heritage of curiosity and resilience is a powerful reminder that we are all part of this ongoing story of discovery. Let this knowledge be an invitation to learn more, to seek out the history written in the constellations above you. If this voyage into the past has captivated you, consider subscribing for more journeys into the world's greatest historical mysteries. We would love to hear your thoughts on these celestial explorers in the comments below.